Hi, welcome back. Let's just move on to the electrostatic side, where basically, once again, just to reiterate, please make sure you know Coulomb's law and are able to state it and to really explain what it's about. And don't worry, in the short question side, I'm going to deal with Newton's law of gravity. I'm going to deal with Coulomb's law of electrostatics similarly. I'm going to deal with that separately to this. But what have we got here? We've got charges on bodies, okay? And we know that a plus charge and a minus charge attract, and a plus and a plus repel, and a minus repel each other. This we know, okay? Now, yes, in the short questions you will be asked, does this repel or attract? You'll be given a field. For example, they will say this and this, and then they will draw that and that, and they'll say, what are those? And you'll say, well, the trick to it is to look which way the arrowheads go. You can see the arrowheads come in. The arrows are always drawn from positive to negative, which means that this must be a negative, that must be a negative, therefore we get a force of repulsion between the two. Okay, that's a typical short question that you get asked, along with one where the ratios change, but we'll do that separately. In this section here, then, we're going to look at charges. Now, the first thing to remember is when a thing is electrostatically charged, okay, there's going to be a force which is applying between the two entities. That's either going to be a force of repulsion or a force of attraction. Now, that force is given by Coulomb's law, which is F equals K Q1 Q2 over R squared. What is that about? Well, there's our two things. It's got a charge of Q1, it's got a charge of Q2, and they are R apart. Seen that before? That's the same as Newton's law of gravitation, isn't it? So in essence, what we've got there is we've got a similar kind of it's going to the inverse square, right? So what we've got here is we've got those two. And what it is if that's a positive and that's a minus, and it's measured in millicoulombs, microcoulombs, nanocoulombs, that is 10 to the minus 9, nano 9, right? Nano, 9, the N. Milli, we all know, is 10 to the minus 3. Therefore, micro must be 10 to the minus 6. Okay, just a way to remember which one is which one. Now, the way to do these, first of all, is to say, well, if I draw it, I don't actually need to worry about the sign. I can ignore if it's a plus or a minus because I've taken it into account. Just before we get there though, very important thing, how did we get a charge onto a thing? Is we moved electrons around, didn't we? So if we know a charge is, for example, 1 times 10 to the minus 9 coulombs, which is 1 nanocoulomb, how many electrons did we do? We would divide that by 1.6 times 10 to the minus 19 coulombs. Why? Because the charge on one electron is that. Okay? So essentially, we've got charge, so that's number of electrons, isn't it? Or you could also say that the charge is equal to number of electrons times charge on one electron, which is, let's say, Q. Okay? Simple. Because each electron you take off and put on puts a charge of that onto it. Right? So what we've got to do is we've got to say to ourselves, that would give us the number of electrons. Now, in these sums, what we're going to do is we're going to be looking at two. We're going to look at the one, which is the force between a particle, two or charged bodies. The other one is an electric field strength, right? Now, in this section, the first part, we've only got the one formula. F, K, Q1, Q2 of R squared, where K is the constant, right? 9 times 10 to the 9. So let us take, for example, that we've got 3. Now, this one is more difficult than ones that you're generally going to see, okay? However, it's worth just going through it because, once again, it covers some of the other elements of physics that we need to talk about. Let us say that we've got a charge, we've got our 3 charges over here like that, right? We've got charge A, B, and C. Like that, and they say that is 4 nanocoulombs, okay? and this is 2 nanocoulombs on top, and at the bottom there we've got minus 6 nanocoulombs. Okay? Right, minus 6 nanocoulombs. And they say calculate the resultant force at C, which means the one we're looking at is this one here. Okay. We're interested in what's happening there. They've also given us a distance apart. They say that's there. They are all, I think they said 200 mil. And this is 200 mil apart, right? Like that, right? And you can see straight away it's an equilateral triangle, so we're going to have angles of 60 degrees, which we'll get to in a second. Now, the way to do this is, first of all, look at what is happening between A and C. So ignore B for the moment. So we're only interested in A and C. There. So we've got 200 mil. What do? Change to meters straight away. And we have a charge there of minus 4 nanocoulombs and a charge there of plus 2 nanocoulombs. The first thing you say is, right, what is going to happen between these two? Because we're looking at C, we keep all the others still. So we move C. What can C do? C is going to be attracted down that line. So there's a force of attraction, correct? So you straight away you go and you say, right, therefore F is going to be 9 times 10 to the 9 times Q1, which is 4 times 10 to the minus 9 times 2 times 10 to the minus 9. Note, over 0.2 squared, and that comes out to be 1.8 times 10 to the minus 6, and it's a force, so it's newtons. So that little force down there is 1.8 times 10 to the minus 6 newtons. Okay, right? That's force A, that's Q, charge Q1, Q2, K, and there's R squared. So, straightforward. Right? Now, what do we do then? Then we go to the other side and we say, all right, let's have a look now and say what happens on the opposite side. Let's just move down a wee bit. Okay, so what have we got? We say, okay. Okay. There we've got that force. So let's now we say, all right, let's look at C and B. And at B, we had minus 6 nanocoulombs. And over here we had plus 2. What do? The first thing we do is we say, right, let's go, what's happening? This is going to be pulled down the straight line to B, isn't it? That's what's going to happen there. So what do? We do exactly the same. We go and we just work out the force. F is equal to K times 2 times 10 to the minus 9 times 6 times 10 to the minus 9 all over 0.2 squared. And what do we get? We get 2.7 times 10 to the minus 6 newtons, right? So now we've got two forces, right? Both are pulling down that way, okay? Therefore, we can now go and say, but okay, hang on, just a mo. I know these two forces. We actually have got a force. Now we look at C. There's C. We have a force pulling there and one there. This is 1.8 times 10 to the minus 9 newtons. And this is 2.7 times 10 to the minus 6. Minus 6 newtons. Okay, minus 6 newtons. And that's also minus 6 newtons. And you know, you fill in the angles. These are all 60 degrees over here. Therefore, 60 degrees, 60 degrees, 60 degrees. And now we've got forces at an angle again. So what do we do when we've got forces at an angle? We just put them into components, right? And we're going to work out the resultant. They've already told us there's a resultant. Therefore, there's going to be an unbalanced force, isn't there, in the system? So let's have a look at it. Right, therefore we go and we say, I have got a force this way, and we just resolve them in components. I've done it already. Force in the vertical, in other words, this is going to be 2.7 times 10 to the minus 6 times sine of 60 degrees, which is equal to 2.34 times 10 to the minus 6 newtons. And this one here is going to be a 1.35 times 10 to the minus 6 newtons. Similarly, we do the same. Remember, opposite again, and we get that one there. We've got 1.55 times 10 to the minus 6, and this one is 9 times 10 to the minus 7. Okay, it's the cos 60, 9 times 10 to the minus 7. So can you now see, what have we got? We've got a force pulling this way of 1.35 and a force this way of 9 or 0.9 if you want to be relative to each other. Okay, so obviously there's an imbalance, there's a resultant. We then add them horizontally and vertically to find this F net, the imbalanced force. So we say, all right, what is it going to be? It's going to be, in this direction, we end up with a force that way of 4.5 times 10 to the minus 7 newtons. And down, we add those two, 3.89 times 10 to the minus 6. Okay, and then I move it always like so to give me my resultant, and my R is going to be the square root of that squared plus that squared, which is going to then come out to be, I'll just write it down. Okay, it comes out to be 3.92 times 10 to the minus 6. Okay, newtons. And theta again is arctan that over that, so it's 83.24 degrees. Okay, so that's how we do them. You just take the two. Okay, it doesn't matter what orientation. As I said, this one is more complex than most. The general one that you're going to see is you're going to see one that looks like this, black. You're going to see one where you've got that, that, and that, and it's going to say at this point here A, B, and C. You then say, if this is say a positive and a minus, that minus is then going to have a force that way. This one will have a force that way. You'd work these out here using F equals K Q1, Q2 over the distance squared. Work out that one, Q1A, Q2 over R squared. That's that force. And then you'd add them together like normal vectors. Okay? Very straightforward to do. Okay, the next one is where we're going to do an electric field. Now remember, electric field strength, the critical thing about an electric field strength, okay, we'll get to it in a sec, okay, is going to be a situation where they're going to give us some charges. In this case, they've said A and B are 2-point charges. A and B. Okay, and they are placed as shown, and there's a distance of 50 centimeters between them. Okay, remember, always got to change to meters, right? That's going to be decimeters is 0.5 meters. Okay, and then they place point C 20 centimeters on the outside of that. Now it doesn't matter if it's on the outside, the inside, or even above, right? You just follow the same rules. First of all, we say, right, let's have a look. We've got a charge here of 12 microcoulombs, okay, 12 nanocoulombs, okay, 12 nanocoulombs here, and at B we have a charge of minus 2 nanocoulombs. Okay, then what do we say now? We say, okay, let us now, they want the field strength at C. First of all, is ignore B. In other words, just draw A and C. We say 12 nanocoulombs positive. There's A and there's C, and the distance from A to C is going to be 0.7 meters, correct? Okay, always change it, doesn't matter what it is, we change it back. So we've got that. Now hang on, we don't know what C is, but remember, the basic rule is you test charge. If you're not given it, you have a little positive charge there, and you see which way the field strength is, right? What's that going to be? Positive to positive means you're going to have a field strength that way, correct? And now I can work out E is equal to K Q1 over R squared, which is going to be 9 times 10 to the 9 times 12 10 to the minus 9 divided by 0.7 squared, which is going to be 220.4 newtons per coulomb. Okay. Now, very often you can work out the unit from the formula, because the formula is E is equal to that. You could go and work that out, but you also know that E is equal to F over Q, newtons over charge, newtons per coulomb. Okay, so that's that. Can you see what we've done? We've taken that. So E here is that way. It's a plus field of 220.4 newtons per coulomb. Right, now what do? We do exactly the same again. And we say, right, now just work with B and C. And B and C are 0.2 apart. B is minus 4 nanocoulombs. This is our positive charge. We're going to have an electric field pointing towards the negative over there. And we then work it out again. KQ over R squared, which is going to be 9 times 10 to the 9 times 2 times 10 to the minus 9 over 0.2 squared, and that gives us 450 newtons per coulomb. So we've got E equal to 450 newtons per coulomb that way. Okay. Now, that means we've got two field strengths, right? We've got two electric fields at that point. Right? Now, remember, the electric field came from, say you had a whole lot of pluses here and a whole lot of minuses here. They were drawn like that, correct? Plus to minus. Okay? That's how an electric field is drawn. So if we've got an electric field this direction, and note, when I use electric fields, I draw 3 lines as opposed to one, which is my force. Okay, in the previous one we did an F. Here I do the electric field strength like that. So we've got an electric field strength that way of 220.4 newtons per coulomb, and we've got an electric field strength. Let's just change the color. It might make it sort of easy. We've got an electric field strength this way over here, E equal to 450 newtons per coulomb. So they're in opposite directions. Now, an electric field strength is a vector, but it doesn't matter if you know that or not. Basically, what have you got? You've got a field one way and a field, so part of it's going to be cancelled out. So the resultant electric field is going to be 450 minus 220, okay, which is going to be equal to 229.6 newtons per coulomb to the left. Because this is the field I'm going to have left, isn't it? Of 229.6 newtons per coulomb. The rest has all been cancelled out. It's like putting batteries in one behind the other, isn't it? Okay. So those are the questions on field strength. Okay. In the next one, we're going to talk about how to answer ratios using Newton's law, and also using the one with Coulomb's law. Okay. That we'll do the next up, and then we'll do a few electric circuits to finalize this whole process.